Hello everybody, welcome into another lesson. So today we are going to talk about the limit of composition of functions. So for our first example, you have find the limit as x approaches 2 of f of g of x when f of x equals x cubed and g of x equals x squared. So we are going to take the limit of a composition. Well, we know from algebra to find the composition of a function, all you're going to do is take that g of x and put that in for where you see x into the f of x. So the classic algebra method is going to be then the limit as x approaches 2 of f of that x squared, which would turn into the limit as x approaches 2 of that x squared raised to the third power. Well, x squared raised to the third power is x to the sixth. So this would turn into the limit as x approaches 2 of x to the sixth. And in this case, x to the sixth is defined for all real numbers, so it's definitely defined at 2. So we can use direct substitution and put in 2 for x. So this would give you 2 to the sixth, which would give you a limit of 64. So the limit in this case would end up being 64. Well, that's the classic algebra method, but there is a little bit of a shortcut we can use. There is a slight bit of a shortcut we can use with one caveat. In general, if you have the limit of some function as x approaches some arbitrary number a of f of g of x, you can say that that's equal to the limit as that's not what I want to say. You could say that that's equal to f of the limit as x approaches a of g of x, provided the limit exists for g of x. So if you're taking the limit of the composition of two functions, if I'm taking the limit as x approaches a of f of g of x, it's the same thing as taking f of the limit as x approaches a of g of x. You can do that if and only if the general limit exists for g of x. If it doesn't exist for g of x, then you have to do the classic algebra method. You could still get a limit, but the shortcut method may not work or the shortcut method won't work itself if the limit doesn't exist for g of x. So let's go ahead here. Let's do this same example, this time using our shortcut method. So the limit as x approaches 2 of f of g of x is going to equal the limit as x approaches, sorry, not the limit, it's going to equal f of the limit as x approaches 2 of g of x, which would end up giving us f of the limit as x approaches 2 of g of x, which is x squared. Well, the general limit definitely exists for x squared. We can do direct substitution for the limit for x squared, so that would just equal f of 2 squared, which would end up giving us f of 4, Well, f of 4, that's going to end up giving us 4 to the third, which also gives us a value of 64. So with the shortcut method, you get a limit of 64, just the same as you would using the classic algebra method. And it really shouldn't matter. You should get the same result, provided that the limit exists for g of x. And this might save you a little bit of algebra. That's the goal of the shortcut method. It saves you some of that algebra work. All right. Now, let's see here. I don't know why I did that. Find the limit as x approaches 0 of f of g of x when f of x equals 1 all over x squared plus 1 and g of x equals 1 all over x. Okay, so we're being asked to find the limit as x approaches 0 of f of g of x when f of x equals 1 over x squared plus 1 and g of x equals 1 over x. Well, okay. Here's the thing. The general limit for g of x, if we go to take the limit as x approaches 0 of 1 over x, we know the general limit doesn't exist. So unfortunately, we can't use the shortcut formula. So what we need to do is take f of g of x. So this would turn into f of 1 over x, which is going to then give us 1 all over, we direct substitute g of x in for that x value in f of x, 1 all over 1 over x quantity squared plus 1. Well, that's going to end up being 1 all over 1 over x squared plus 1, which would simplify further into 1 all over 1 plus x squared all over x squared. Now we have a complex fraction. We just invert and multiply. You would end up then getting, let's see, 1 over 1 plus x squared. Or really, this would be 1 over 1 times x squared all over 1 plus x squared, which would end up giving you x squared all over 1 plus x squared. Now that we found f of g of x itself, let's take the limit as x approaches 0 of that. So the limit as x approaches 0 of that x squared over 1 plus x squared, well, we can use direct substitution, because if we put 0 in the denominator, we'll just get a denominator of 1, which is definitely defined. If we do direct substitution, you would get 0 squared all over 1 plus 0 squared, which is just going to give you 0. So in this case, we have the limit of f of g of x being 0, but we were unable to use the shortcut method because the general limit did not exist for g of x. So that's something you have to check. Don't just blindly use that shortcut method. All right. Let's do a couple more. Find the limit as x approaches pi of f of g of x when f of x equals the inverse tangent of x and g of x equals the cosine of x. All right, we have a good one here. We have an inverse trig function we have a trig function going inside of an inverse trig function. So find the limit as x approaches pi of f of g of x when f of x equals the inverse tangent of x and g of x equals the cosine of x. Can we use that shortcut method? Well, the general limit as x approaches pi for cosine of x actually does exist, and we know that that's going to be -1. So yes, we can use the shortcut method. This will turn into f of the limit as x approaches pi of the cosine of x. Well, as x approaches pi of cosine of x, that's going to be -1. So you'll end up getting f of -1. Well, the f function is the inverse tangent, so that would be the inverse tangent of -1. And we know then we should end up getting a value of -pi/4. So you should end up getting a limit of -pi/4 using the shortcut method for that inverse tangent function. So yes, that's a very neat trick. Let's do one more where I'm going to lead into it and say that we can't use the shortcut method in this. So let's see. Find the limit as x approaches 0 of f of g of x when you have f of x equal to e to the x and g of x equals the natural log of x. Alright, so we have an exponential and a logarithmic function. So we're being tasked with finding the limit as x approaches 0 of f of g of x when f of x equals e to the x and g of x equals the natural log of x. Well, can we use the shortcut? Well, the general limit we know of the natural log of x as it approaches 0 does not exist, because the natural log is not defined for any values of x less than or equal to 0. So unfortunately, that shortcut method is not going to work. But we can use the classic algebra method. So if we want to find f of g of x, well, that's going to end up then being f of the natural log of x. Well, the f function itself is e to the x, so this would end up being e to the natural log of x. If we remember from algebra, if you take e to the natural log of x, the base e's cancel out, you're just left with x. So we found f of g of x to be x, so now this just turns into the limit as x approaches 0 of x, which we know we can use direct substitution and get a limit of 0. So the limit in this case is actually 0 by using the classic algebra method. So keep in mind, when doing the limits of compositions of functions, the shortcut method only works if the limit of your inside function exists. If it doesn't, if the general limit doesn't exist, you have to revert to classic algebra. So that's going to be it for this lesson. The next lesson we're going to talk about the intermediate value theorem, which is a very good theorem too from calculus. That it's a very good calculus theorem that's going to help you. So I hope everybody has a great day. Take care.